Welcome. Today we start talking about groups, and to do that, we first introduce binary operation. Let G be a set. A binary operation on the set G is a function star from G cross G into G. Now recall that G cross G is the Cartesian product of G and G. That is, G cross G is the collection of all ordered pairs of elements of G. So, so that is each element of each pair of elements of G is assigned exactly one element of G. Right? That's what the function does here. This function is this function assigns to each ordered pair of elements of G exactly one element of G. And instead of using the notation star evaluated at the input AB, which is the usual function notation, we use the notation A star B. Addition and multiplication of integers are examples of binary operations, and in the usual multiplicative notation, we write A dot B instead of writing dot evaluated at the pair AB, and also we write A plus B instead of writing plus evaluated at the pair AB. So in other words, we usually write 3 times 5 instead of writing multiplication evaluated at 3, 5. And we usually write 3 plus 5 instead of writing plus evaluated at 3, 5. So what is a group? A group is a set G together with a binary operation star, and usually the operation is called multiplication unless otherwise we say that it is addition. So a group is a set G together with a binary operation that satisfies 3 properties. Property number 1 is associativity, which means the following: if we are multiplying a sequence of 3 elements A, B, C, and G, then we have a choice of where to put the parentheses. So here we are applying the operation to A and B first, and on the other side we are applying the operation to B and C first. So on the left hand side, star is applied to A and B, and then star is applied to the result of that and C. On the right hand side, the star is applied to B and C first, and then star is applied to A and the result of B star C. And so if we are multiplying a sequence of 3 elements A, B, C, and G, then this property tells us that it doesn't matter where we put the parentheses. Property number 2 is that there must be an identity element. That is, there must be an element E in G such that A star E and E star A are equal to A for all A in G. So E here is called an identity element in G. And then the third property says each element of G must have an inverse. That is, for each element A in G, there must be an element B in G such that A star B is equal to B star A is equal to the identity E. So a group G is a set together with a binary operation satisfying these 3 properties. Now, if a set G is given together with a binary operation, to show that that's a group, we always should also check the closure property that whenever AB is in G, A star B is in G, to make sure that we have a valid binary operation. So we're going to use the notation G comma dot within parentheses to denote a set G equipped with a binary operation dot. Now instead of dot, I may use star, I may use a plus or something else. Pay attention to what notation is used for the group operation. Are we using the additive notation or are we using the multiplicative notation for the group operation? Usually we are going to use the multiplicative notation for the group operation. Now, what is an abelian group? An abelian group is the following. So a group G is called an abelian group or a commutative group if AB is equal to BA for all AB in G. Here I'm using multiplicative notation for the group operation, and if we are using the multiplicative notation, a lot of the times we skip the dot. Now if there is some pair AB for which AB and BA are not equal, then we say that G is not abelian. I guess I didn't finish, I didn't complete the sentence here. So we're going to start with our first example here. So again, abelian group is a group that additionally satisfies this commutative property that AB is BA for all AB in G. Now if I use additive notation here, then I would be saying A plus B is equal to B plus A for any A, B in G. Okay, so here's my first example. Let's take S to be the set of all real numbers except -1. So this symbol means from the set of the real numbers, get rid of -1. So this symbol here is set minus. So we define star on the set S in the following way. So for any AB in S, A star B is equal to AB plus A plus B. Now AB is the usual multiplication of A and B, and plus is the usual addition in the set of real numbers. So AB means the usual product of AB in the set of real numbers. So we are defining this new operation in terms of the usual multiplication and addition of real numbers. We want to prove that S is an abelian group under this operation star. Okay, so what do? Well, we have to prove the three properties of a group first, and then we have to also establish because we want to show that S is an abelian group, we also have to show that it satisfies the commutative property. So let's first show that star is associative. So let's let A, B, C be arbitrary in S, and let's look at A star parenthesis B star C. So by definition, what is that? So by definition here, so in here now B star C is the second element and A is the first element. So it is going to be A multiplied with the second element and then plus the first element plus the second element. So it'll be okay, so what I'm doing is I'm writing B star C first. So what is B star C? B star C would be BC plus B plus C according to this definition. So you multiply the two elements and then you add the two elements here. So now what is A star BC plus B plus C? Well, now you multiply A times that, the quantity in parentheses, and then A plus this quantity. So now I get A times BC plus B plus C plus A plus BC plus B plus C. Now let's multiply out here and then rearrange the terms. So if I multiply out here, I get ABC plus AB plus BC plus AC plus A plus B plus C. So A star parenthesis B star C is equal to this quantity. So now let's calculate parenthesis A star B star C. So what is A star B? Well, A star B is AB plus A plus B. Okay, so what is this quantity in parenthesis star C? Well, by definition again, it is you multiply the quantity in parenthesis with C and then plus this quantity in parenthesis plus C. Once again, we multiply out here and then we're going to rearrange the terms, and you see that you get the same quantity ABC plus AB plus BC plus AC plus A plus B plus C. So we see that A star parenthesis B star C is the same as parenthesis A star B star C, and so the star is associative. Okay, so that's the property number one. Now so here I wrote down the set S again, and then what is the operation here again. So now we want to ask, is there an identity element in this set? That is there an element E such that A star E is A for all A in S? Well, let's see. So let's let A be any element of S, and we want A star E to be A. And from this equation, I want to solve for E. Well, what is A star E? Well, A star E would be AE plus A plus E. So that must be equal to A. Now from both sides we can cancel out A, and then we get AE and E here. So if I factor out the E, then I get E times A plus 1 is equal to 0. Again, we're getting 0 because this A and A here cancels out. So now I see that E, remember that A belongs to S, so A cannot be -1. So because A is not -1, A plus 1 is not 0, therefore E has to be 0. So E is 0, so that's the identity element. So we found an element in S such that A star, we have found an element E in S such that A star E is equal to E for all A in S. And now we can also check that E star A is also A for any A. So if I take E to be 0, then this equation is satisfied for any A. So we found that the 0 is the identity element in this set. Next, we want to check if every element of S has an inverse. Well, given A in S, is there an element B such that A star B is the identity 0? Well, let's say A is given, A is fixed, and we want to solve for B from this equation, A star B is equal to 0. Well, then AB plus A plus B is equal to 0. And we can take A to the other side, and AB and B, from this two we can factor out the B and write B times A plus 1. So AB and B gives me B times A plus 1. A goes to the other side is -A. So remember, A is an element of S, so A is not -1. So because A is not -1, A plus 1 is not 0, so I can divide both sides by A plus 1. So we see that B is equal to -A over A plus 1. And so that's the inverse of A. So what's the inverse of A? Well, the inverse of A is -A divided by A plus 1, and which is a real number that's not -1. And so that belongs to S, so we conclude that we see that every element of S has an inverse, and so we have established associativity, we have shown that there is an identity element, and we have shown that every element has an inverse, and so S must be a group. But we wanted to show that S is an abelian group, so one more property that we have to establish now is that star is commutative. And to do that, we have to just show that A star B is the same as B star A. Now A star B is AB plus A plus B. and B star A is the same as BA plus B plus A by the definition of star. And we know that this is the AB and BA, that's the usual product of real numbers. So we know that AB and BA are the same. So we see that A star B and B star A are the same, and star is commutative. So finally, we can say that S is an abelian group. Okay, so here's an example. Here I'm taking A to be the collection of all functions f, m, b from R to R, where m and b are real numbers, m is not zero, f m b of x is mx plus b. And these functions are called affine functions. And if you look at them, these are actually the linear polynomials. So by making sure that m isn't zero, so remember that m would be the slope of these are all straight lines, right? So by saying that m is not zero, we are only picking straight lines with non-zero slopes. And recall that straight lines with zero slopes are horizontal lines, and they don't have inverses. So the straight lines with non-zero slopes, they are all increasing or decreasing, and therefore they are all one-to-one, and they have inverses. So this set is a group under the composition of functions. And we already know from calculus that composition of functions is associative. E of x is equal to x is the identity function here with respect to composition. And what would be the inverse of the function fmb of x? Well, the inverse of this function would be the function f1 over m comma minus b over m of x, which is 1 over mx minus b over m. And again, you can go ahead and check that this is indeed the inverse of this function. The Z is not a group under subtraction because it's not associative. So for example, notice that 7 minus, if I have the three numbers 7, 5, and 2, and then I'm subtracting these three numbers, then notice that it does matter where I put the parentheses. So if I put the parentheses around 7 and 5, then minus 2, then what do I get? 7 minus 5 is 2, 2 minus 2 is 0. So on the left hand side I have 0. Now if I put the parentheses around 5 and 2, then 5 minus 2 is 3, and 7 minus 3 is 4. So that's not the same as 0. So you can see that subtraction is not associative. So Z is not a group under subtraction. If I look at the, so M22, that is the collection of 2 by 2 matrices, and the set of 2 by 2 matrices is a group under component-wise addition. What about under matrix multiplication? Well, the set of 2 by 2 matrices is not a group under matrix multiplication because not every matrix has an inverse. Now, if I take the set of all 2 by 2 matrices over the real numbers, if I take the set of all invertible 2 by 2 matrices over the set of real numbers, that's called the general linear group of degree 2, and it is denoted by GL2 of R. So if I take the set of all 2 by 2 invertible matrices, then that forms a group under multiplication. Identity matrix will be the identity in the group, and each matrix here will have a multiplicative inverse. And also the set of all invertible n by n matrices over the set of real numbers is called the general linear group of degree n, and is denoted by GLN of R. Is Z10 a group under multiplication mode 10? If not, does it have a subset that is a group under multiplication mode 10? Well, Z10 is not a group under multiplication modulo 10 because, for example, the number 2 doesn't have a multiplicative inverse in Z10. So recall that Z10 star is the set of all invertible elements of Z10. So these are the elements that are relatively prime to 10, and each one of them has an inverse. And so this is a Z10 star is going to be a group under multiplication mod 10. And there are a couple of other questions in this set of exercise, and in this set of exercises. So I will let you figure those out. Here are two more examples. So if I look at R to the n, so this is the set of all n tuples, and this is a group under a component-wise addition. If I let G to be the set of all TAB, where A and B are real numbers, it consists of all functions TAB from R2 to R2, defined by the following assignment. So the input xy is assigned to the output x plus a comma y plus b. So basically you are translating, this is basically a translation by a units in the x direction and b units in the y direction. And if I, so the set G, the set G is an abelian group under composition of functions. And to see that it is closed, note that if I take the composition of TAB, I didn't write down the composition symbol here, but the composition of TAB and TCD is equal to TA plus C comma B plus D. The inverse of TAB is the function T minus A minus B. So TAB is the translation by A units in the x direction, B units in the y direction. So the inverse is given by the translation, which is translating by minus A units in the x direction and minus B units in the y direction. Elements of G are called translations, which I already mentioned. This again, you can check the details that G is a group under composition of functions. Is an abelian group. SL2 of R. This is the set of all this is the set of all 2 by 2 matrices over R with the determinant 1. And this is going to be a non-abelian group under matrix multiplication. It's called the special linear group of 2 by 2 matrices over the set of real numbers. This shouldn't be an F. This should be the set of real numbers here. The inverse of the matrix ABCD. This should be a D here. ABCD is the matrix D minus B minus C and A. So notice that basically the diagonal entries are switched, and then we reverse the sign of the off diagonal entries to get the inverse. Okay, so I'll stop here. In the next video we will be proving some theorems.